Hello everyone and welcome to yet another recreational programming session with Mr. Zuzin as usual. So it's going to be an offline session, right? So because I don't anticipate it to be very long because I just want to quickly check some quick ideas, so I don't think it's worth to start up an entire online stream or anything. So on the previous sessions we implemented an algorithm called byte pair encoding. It's a very simple algorithm actually. You have a text and what you do is that you pick a most frequent pair, right? And you replace it with an unused byte. And then you repeat the process compressing the text until you can't compress no more, and you have this sort of like a table. So this kind of algorithm is used for deriving a tokenizer for large language models and stuff like that. So, and we implemented it. And then we try to parallelize that, right? So because effectively what you can do, you can split the text into several chunks and you can process those chunks in separate threads and then merge the results of the processing together. It's sort of like in a MapReduce style, as somebody in the comment section said in the previous video. Right, but the problem is that I tried to apply this improvement on a big text that I have, which is the log of our Discord server is actually 33 megabytes, I think. Yeah, there we go. So I have like a Discord logs in here and it's 33 megabytes. And it's still very long, right? So I couldn't wait until the end. It's like several hours and it's not even close to being processed. Even though it was an improvement, it was, I think, roughly 2x improvement. We can actually measure it. We can actually measure it. So I have a tool. Right, so which is called txt to bpe, right? So I have some prepared command line arguments in here. So we can take a look at the arguments, right? So I improved it a bit, so I actually made a lot of parameters customizable through the command line utility and stuff like that. So essentially what we have to do, we have to provide first the input file that we're going to be compressing, right? So this is going to be Discord log. And then we have to provide the output directory, right? So, and essentially the reason why it's an output directory and not the file, as in the previous session, is that I implemented so it snapshots the current state of the process every few iterations, right? So you can customize like how frequently it does the snapshot. So since the process is rather long, right, maybe several hours or so, you may want to actually check out periodically how the current state is doing, right? So just check the currently identified tokens and how much the text is compressed and stuff like that. So what it does, every few iterations is just like dumps its current state that you can then, while the iterations are going, just like check out and like see if it's going in the right direction and stuff like that. Right, so and also let's actually reduce the amount of iterations, right? So it's going to go for very long. It's like over 100,000 of iterations, right? So it's going to be like several hours. Let's limit the amount of iterations to 100, right? So, and let's actually try to run it. Maybe I'm going to go ahead and disable the threading mode just to see like how slow it goes without any threading. So let's go. So this is going to be basically 100 iterations and it's going to be dumping its state every 10 iterations. So this is the first iteration. And yeah, essentially one iteration takes half of a second, right? It takes half of a second. So which is rather slow, right? Because during that one single iteration, it needs to iterate through all of the tokens of the text, identified all of the frequent ones, then replace them, and so on and so forth. So it's pretty slow, right? I'm not even sure. Yeah, it's actually getting closer to 100, right? So we're already at 60. So as soon as it reaches 100, we're pretty much done. So let's just wait a little bit more. So my CPU is actually spinning up. I can hear the fan spinning up. And yeah, and we're done. Right, so here we have basically, you know, snapshots of the state for every 10th iteration, essentially. So, and it's a single-threaded one, right? So let's actually mark it as a single-threaded. And now I'm going to enable maybe it actually makes sense to save the log. I didn't think about that. This is actually a very cool idea. What if we also save the log? So we can actually see what the fuck is going on. So this is going to be Discord log st txt, something like that. This is a cool idea. I really like that. And now let's actually go to txt to bp and enable threading and see how better it is going to go. Right. So let's actually restart it. So let's wait a little bit. And as you can see, now the time of a single iteration is, you know, 170 milliseconds first with a single threaded mode was half of a second. Now it's around like 150, right? It's an improvement. It's a 2x, and it's already finished, by the way. It is definitely an improvement. It is definitely an improvement, but it's not that big of an improvement. It's still very fucking slow. Right, because we're also like deallocating and recreating the hash tables over and over again, and it's kind of a painful process. It would be kind of cool to find a way to not recreate the hash table over and over again. So maybe that will speed it up. Okay, so let's actually mark it as multi-threaded. So we have a single-threaded and multi-threaded. Let's save the log as well. Right, so, and this can be Discord. So let me find the log. Can I just like empty txt? There we go. So we have also this kind of log. So, but after the session where we did multi-threaded implementation in our Discord server, so let me actually find the message where we had a discussion about that. So let me quickly open it up. Discord is insanely slow. So Isel Gray, right, so suggested a pretty cool idea. I think that maybe rebuilding the frequency table is kind of a waste of time. You could, in a step of replacing most frequent pair, for instance A, B, C, D, A, Z, modify the hash table removing appearance of A, B, and C, D for each substitution and add A, Z, Z, D to the hash table. So this is actually a pretty cool idea. So essentially you do not recompute the hash table over and over again, right? So if you identified the pair that you want to replace, you basically in place update the table. That's what you do. You just in place update it. But this approach is actually not particularly parallelizable, I think, right? So I don't see how you can split this work into several chunks and put it on several threads. But maybe it's not even needed to be like that. Maybe it's going to be faster than multi-threaded solution anyway, right? So you don't really need to parallelize it. Some problems are just not parallelizable like that, especially when like result that you're currently computing kind of depends on all of the previous results, which is also the case in here, I think. I think it is the case in here. So anyway, let's actually give it a try and see if it's going to improve anything. So txt to bp. All right, so let's disable the threading. I'm not really sure if it's important to disable the threading or not. Okay, so here's the single iteration. So within the single iteration, first of all, we free the hash table. We don't have to free the hash table, right? And then depending on whether the threading is enabled or not, we're collecting the frequencies of the pairs either in a multi-threaded mode or in a single-threaded mode. It doesn't really matter like which one is enabled in here. So we might as well. So we disabled this thing, yeah, we disabled this thing, so we're going to be using a single-threaded mode. We only have to do that once, right? That's kind of the whole point. This thing that we're doing on each iteration, we only need to do once at the beginning of the process, right? So we don't have to clean anything. Maybe we can, we don't have to clean anything. So, all right, so we computed it once right before starting everything. Then we're iterating through the hash table and finding the maximum pair, the maximum frequent pair. That's what we're doing in here. So, and then if the frequency of the most frequent pair is basically 1, or you can actually customize that, right? I recently added that you can stop the process with a custom termination pair frequency, right? So maybe you stop at like 5, right? So it's not gonna go for too long, right? I haven't used it yet, but I thought maybe it's a good idea to have this kind of option. So then you add the maximum pair to the pair table, and then you start the replacement. And this is where we have to do all of that stuff. So the problem with this algorithm, even though on the paper it sounds kind of cool, it's actually in reality rather complicated because we're iterating the pairs from left to right. So that means to the left we have things that we already kind of replaced, and to the right we have things that we have not replaced. And the way we replace that is actually we take the tokens input, right? So this is our array of tokens. We iterate it from left to right and append whatever we want to append to the output tokens. And if we are about to replace some pair, we just replace the pair with the new token in there. Right, so essentially, so we have something like A, B, C, D. So, and this is in the input tokens, and here we have output tokens. So we encounter A, right? So A, B is not the most frequent pair, so I just append A. Then I encounter BC. Let's assume that BC is the pair that I want to replace. Right, so because of that, I have to actually subtract the frequency not of the A-B pair, but B and whatever we have in the output, because maybe we have something that we already replaced in here, right? So essentially, when in this entire process we look into the past, we must look into the output, but when in this process we look into the future, we have to look into the input. Right, so we have to be super careful in here, and the reason why I didn't implement this algorithm right away is because how finicky it feels, right? A lot of corner cases, and I absolutely hate this kind of algorithm when there's a lot of small little corner cases, but unfortunately, these kind of algorithms are usually the most performant ones, right? So the most performant algorithms are the ones that are the most annoying to implement. But maybe if the, if we're gonna win a lot of time by just using this algorithm, maybe it's gonna worth it, right? Maybe it's gonna worth it. But anyway, so let's actually take a look at different cases in here. And what's funny is that we already have a bunch of cases in here, right? So here's one case, here's another one, and here's the third one, right? So we have 3 different cases in here. So what's the first case? When I plus I, so the current character I plus 1 is greater than the amount of tokens we have, we just append that into the output and we continue. So this is basically checking for the last character. Are we looking at the last character? If we're looking at the last character, there's nothing much to replace because you don't have a pair in here, right? So we identify a pair by looking into the future by 1 token. Right, so that's how we identify. If your last character, if your last token, like there is nothing in the future, there is no pair in here. So we just append it to the output and we just die. In fact, we could have actually written this entire thing something like this, right? And it would have made a little bit more sense, right? So basically unnested. So because after doing this kind of thing, you're gonna exit anyway. Right, you're gonna exit anyway, but what I did, I essentially let this condition exit the entire process. So I'm not really sure if it's a good idea to do it like that, but yeah, so let's just keep it as it is. Okay, so the else branch is when you do have some token in the future, and there you go, here is the pair, here's the pair that we're looking at. So essentially we're comparing that specific pair with the most frequent one. So maybe it would be actually kind of cool to maybe factor out. Yeah, let's actually factor out this entire thing to something like max pair. Right, so here's the max pair, and so now we can actually do something like max pair. There we go. So this is a max pair. If the pair that we found is equal to max pair, this is what we have to modify now, right? So this is what we have to modify now. If it is not the pair, we just append the current character and we move on. I don't think we need to modify anything in here, right? So this is a situation when we do have a pair, but it's not the pair we're looking for. This situation is when we don't have a pair, right? So I think it makes sense. So anyway, so let's actually bring this entire thing in here. I think it's going to be very useful. So we're essentially basically looking at this kind of thing, right? So we're looking at this kind of situation. So first of all, we need to subtract the frequency of the pair AB, but we have to actually look at A from the output, not from the input. But here's an interesting thing. What if we don't have anything in the past? Right, what if we don't have anything in the past? We need to specifically check for that case, right? So when we don't have anything in the past, it's when I is equal to 0, it's one way to do that, or when tokens out is actually, equal to 0, right? So because we didn't append anything there, it's kind of equivalent, two equivalent conditions. So in here we can say the following thing: if you have something in the output, that means you have something in the past to look at, right? You have something in the past to look at. And essentially here we already have a pair that we can kind of utilize. So the left character in here is going to be the last character of the output. So let's actually take items and put count -1. So this is the left one. And the right one is going to be the current one in the token's input, right? So this is going to be something like that. There you go. Here is our pair. Here's our pair. So now we need to look up that pair in a frequency table. So I think it's something like get I. I'm going to put it in here. So we need some sort of variable where we're going to hold an index to the bucket. So here's the frequency and we provide the pair. All right, but here's an interesting thing. will that pair exist? If it occurs in the output, that means it does exist in the table. So we can actually kind of assert that place is greater or equal than 0. Because if it isn't, that means we made a mistake somewhere. Because in this particular situation, that pair must exist in the table, right? It must exist in the table. Okay, so after that, we just take this specific pair and we decrement this counter. What's interesting now is that since it exists in the frequency table, right, its counter has to be greater than 0. It has to be greater than 0. So this is another condition that we can actually double check in here. Again, if it's not the case, that means we did something wrong like previously somewhere in the algorithm. I think since it's a very finicky algorithm, it is very important to put as many asserts here as possible to make sure that we don't have any inconsistent state, right? So anyways, so we process this kind of thing. So we subtracted AB, right? Essentially we subtracted AB. Now, since we're going to be replacing BC with Z, right? So this is our replacement equal BC. We need to increment the pair AZ, right? But that means we need to create a new pair in here. So the pair is going to be left equal to this, right? So again, this is basically A. And the right one is going to be the maximum pair. The maximum one is it's basically the counter. The counter of the pair is -1, so it's this one. So essentially we even append it into the output in here, right? So we can basically take this one. Maybe it makes sense to factor it out to a separate variable, honestly, because it's kind of dangerous. So let me quickly do that. I'm going to put it somewhere here. So let's actually call it something like max token. So there we go, max token. Or we can actually put it before we append anything into the pairs and remove -1, right? Because it's essentially -1 in here before you, so I think that's even better. That's even better. So this is a maximum token. This one becomes kind of a max token as well in here. So that's pretty cool. So honestly, since this one is the same thing, maybe it makes sense to not do that, right? So just like, we're just setting it once and only modify the left one and the right one. So we're just setting left, and here's the when it's the right one, and here is so that makes sense. Anyway, so let's now look for this kind of thing. And this one, by the way, might be missing because we just introduced a new token. So you may not have that pair in the hash table. So that means you may have a situation when the place is actually negative, right? So there is no such thing. In that case, I think what we have to do, we have to add a new pair, a new entry into the hash table. So we're going to do hputs, frequency pair, and since it's one pair, it's the first pair that we encounter, so its frequency is 1. Okay, so if you do have that pair before, if you already replaced it before, I think it's like you just increment it, right? So it's going to be place value, just incremented by 1. Right, in this particular case, we don't have to worry if it's like, greater than 0 or not, we're just incrementing it if it exists. So, all right, so we basically processed this case, right? We essentially processed this case, but there is a lot of more, right? So now we have to decrement this pair, right? Then we have to decrement this pair, and then we have to increment this pair. There is a lot of cases in here, so as you can see. That's why I didn't want to implement this algorithm, because it's just like, it's so many freaking cases. Anyways, so in here, let's take a look at that. So here we need to look up the maximum pair, right? So we already kind of have this kind of thing. So place, let's actually maybe declare this variable somewhere here and keep reusing it throughout sort of like the body of this thing. So I need to hm get I max pair in the frequency. Right, and I think since it's the most frequent pair, it must exist in the frequency table. So this is basically, we have to do assert place greater than equal, there we go. And also, since it exists, its frequency actually has to be greater than 0 because we're going to be decrementing it. Maybe another thing that we want to do in here is if this entire thing becomes equal to 0, we have to delete it. So not to consume too much memory, and so that the memory can be reused, but I'm not really sure. So you know what, I think I'm gonna just do something like this. So it's gonna be frac, and this is the pair, and I'm gonna put to do in here because I'm not really sure. Maybe it's not gonna grow too much. We'll see. All right, so we decrement this entire thing, so everything's Gucci. Okay, everything seems to be Tamaguchi. So after that, we are incrementing the counter, right? So we are appending that z to here, and we incrementing this entire thing by 2, right? We're incrementing this entire thing by 2. So I suppose after that, we have to work on this part of the algorithm, right? So we have to decrement this pair, right? And then increment pair zd. So that's what we have to do. That's what we have to do. All right. But here's the thing. You may actually have a situation that after like advancing the cursor, you can go outside of the input. And in that case, you don't really have, you know, any pair in the future to process, right? So it's kind of a similar situation to the past, like in here, but now it is in the future, right? So it's kind of similar to that. So I suppose what we have to do in here is just basically check if I is greater or equal to the tokens input, right? So this is going to be count. Only then we consider this entire thing, right? So every time we consider past and the future, we first check, do we even have past or do we even have future? I think it's kind of important. So let me actually bring this entire, like that's a lot of code already just for this small freaking thing. God damn it, like, and we haven't even, this is like half of the idea. This is only half of the idea. Like, this is a very small description of an idea, right? And this is how much code I have to write to make sure that, you know, like everything is correct and stuff like that. And of course, AI bro is gonna say, oh, just put that into LLM is gonna write that code for you. So anyways, all right, so we have this kind of thing. So we're looking at that stuff. Right, and we know for sure that we have the pair in the future. So what kind of pair do we have in here? So the left one is tokens in items I-1, right? So this is this one. And the right one is going to be the current one. So we have to do in here, we have to subtract it. And what's funny is that subtracting this entire thing is kind of similar, right? So it's basically this code. Like you get the pair, you check that place is greater than 0 and the frequency is greater than 0, and then you decrement it. And it's kind of the same regardless of what you do in here. So maybe you might as well just, you know, copy paste this entire stuff. Copy paste this entire stuff and just like put it in here, right? So this is the decrement. All right, so an increment is going to be essentially the left one becomes the tokens, right? So it's the last one, right? So the last one in the output is going to be items and the count -1, and the right one is going to be again the same, I think, right? So the right one kind of stays the same. So it's only the left one that is changes. So maybe we can do something similar in here, right? So right one stays the same, left Y keeps changing. And for this one, we just have to increment it. So in that specific case, I can copy paste this code, right? So there's a lot of kind of code in here, but it's kind of repetitive actually, if you think about it. Yeah, so this is not what we wanted in here. So I don't know why I copy pasted the thing. So I think that is it. Did I miss anything? Right, so this is for the left part, this is for the middle part, and this is for the right part. So that's what it is. That's what it is. And we don't do HM3 anywhere. We just like keep reusing the whole thing over and over and over again. Okay, so let me try to maybe compile the whole thing. And why did it compile first try? Okay, so yeah, let's give it a try. So maybe it's going to be a completely bogus actually. So bogus. Let's start with something simple. Let me save this specific prompt. Right, so I'm going to start with something much simpler, txt to BPE. The input file is going to be data and just like a small paragraph from Wikipedia. So the output dir is going to be the same name, BPE Wikipedia def. And let's fucking go. Okay, so and it completely fucking failed instantaneously. Insta-fucking-taneously. That's very interesting. So something didn't exist in here at all. Did we not append properly things? Because that's kind of weird. That's kind of absolutely weird, because you telling me that this thing doesn't exist. Like right away. Assertion place. It's like right here. Okay. So let me maybe take a look at this kind of thing. So what's the pair we're talking about? What's the pair? So the pair is going to be something like U, new line, pair L, pair R. And let's just actually abort in here. So let's also print the location, right? So because the assert prints the location in here, I don't really want to lose that information. So it's going to be a file. This is going to be a line, like so. And what do we have in here? Oh yeah, so there's this thing that if you already, like if the folder that you provided, output folder, already exists, it tells you that you may lose some data in here. So either rename it or delete it, right? So this is actually happened to me several times, so I kind of created this sort of like a mechanism, safety mechanism. All right, 256, and yeah, this one is kind of weird. Like, what the fuck is going on in here? Maybe something wrong happened in here as well. So this is the max pair. Max pair, and we do not modify it. Yeah, this is exactly what I'm talking about, right? It's just like too finicky. It is too goddamn finicky. So this is the last one, and this one we just increment. And I wonder how many iterations so far has happened in here. So we can actually maybe even print like I, and see what's the number of the iteration we have in here. Yeah, of course, let's not forget to remove this entire thing. Right, what do we have? So yeah, so we went pretty far with this entire thing. We went rather far, and we still don't have this pair. We still don't have this pair in here. Where did I fuck it up? Where did I fuck it up? I'm not sure. So at some point it simply doesn't exist. It's something stupid, right? So this is why I hate this kind of algorithm, because for me it's super easy to just like forget some small little detail, right? Because it makes sense, right? So the entirety of the thing kind of makes sense. So yeah, let me actually maybe do something like this. I think it's going to be a little bit easier for me to read. So this is the left one. Right, so this is the right one. So this is the current one and the plus one. Okay, so if you have something in the past, right, so we just take in the last value, and then the right one is the current one. We're querying it up. Right, we're making sure that that exists. So that's what this thing actually about. And if it's greater than 0, we decrement it. So now the right one is the maximum token, right? So is the maximum token a correct thing? It is pairs count before we appended a new pair in here. That makes sense. So now we're looking it up, and then if it doesn't exist, we add that pair with 1. If it does exist, we just increment it by 1. Okay, so in here we're looking up the maximum pair. You know what I'm gonna do? I'm gonna actually replace this with something like pair, max pair. So then the code that is responsible for querying up the thing and decrementing it look kind of the same, right? So because here we do pair and here we're doing max pair, so they didn't correspond to the same thing. All right, so this one is kind of fine. And what we do, instead of appending like the original character, we append the max token and we skip like 2 in here. We kind of skip 2 in here. Okay, so for the right one, tokens in, it's this one. For the left one, tokens in previous one, because that's the one that we're going to be decrementing. Okay, makes sense. Now for the left one is the one that we just appended into the tokens. Right, so, and yeah. Bro, I don't see the mistake. I don't fucking see the mistake. Anyway, so let me see. So maybe we could actually start with something goddamn simple. So let's have a small text in here. So it's gonna be A, B, C, B, C, D. Right, something like that. Can you just freaking compress at least that? Debugging this kind of algorithm is just like, it's a nightmare, at least for me, right? So maybe there are smart people out there that can actually maintain a super complex mental model of things. But for me, if there's too many small corner cases and details, I just like, my brain melts down and I can't keep track of that, unfortunately. And I'm like just actively trying to avoid this kind of algorithm. Okay, this is actually kind of cool that we managed to reproduce that on such a small input, because I can do a lot of cool shit now. For instance, I can maybe print the ins and outs and every single iteration. So that's something I can do. Right, so on this first iteration, so let's actually do something like size G, 0 less than tokens in count plus J. Right, so and in here, I'm going to just like print each individual tokens in items J. Right. And in here, we're gonna actually put a new line after all of that stuff. So maybe it makes sense to put like curly braces in here. I want to keep it like a single line, so it's super easy for me to just comment it out. Right. So might as well just do printf. So this is the input that we're dealing with. This is the input. All right, and I need to not forget to delete this kind of thing every single time. All right, so it went through like 3 iterations, but it's not really that interesting because what we're interested in is output. Okay, so this is the output. And here is the output. All right, so what do we have? How do you even append Scheisse to the output? Of course, like, yeah, so it's a safety mechanism, but it's kind of annoying sometimes, but I don't know what could be better in here. Okay, so, all right, and then something went horribly wrong in here. Right, it managed to successfully, look at that. So this is the most frequent pair, 98, 99, right? So this is the most frequent one because there's 2 of them. And it managed to successfully replace this one, but then it kind of failed afterwards, right? It failed afterwards, and it actually, yeah, it failed like precisely in here. That is rather interesting. So yeah, on top of this thing, we can also print the hash table. Who said we can't do that, right? So we can just like check the hash table itself. So let's do something like this, maybe printf. Maybe we can do that on a new line. So size t, and then less than hm length of the frequency table plus I. And here it's going to be just something like this. Yeah, and this is going to be the frequency. Frac I left, frac I right, frac. This one has to be actually the key. And this is I. There we go. So, and don't forget the new lines. Don't forget the new lines. All right, so kind of fucked up some stuff, but this is because it's a ptr div t. All right, and let's not forget to remove the folder. Let's fucking go. Okay, so what do we got? Okay, so this is reasonable. This is reasonable. Okay, after we inserted this thing, did we increment this part? Yes. In fact, here is the 97 to 156. 98, 99 worked beautifully. It decremented by 1. That's perfect. Then 97 to 256. Okay, it was incremented by 1, but I don't see the second one, 256.99. This is where something fucked up in here. This is where something fucked up in here, and that means it's somewhere here. I see. So the condition has to be the like, okay. God fucking damn it. Right, so I'm glad that I managed to find it actually relatively quickly, right? I managed to find it relatively quick. Can I now maybe turn off some of this stuff, right? So there's a lot of code, and if I try to run it on like big amount of data, it's gonna blow up. All right, so can I just put it like that and just comment out? So and if let's fucking go. And of course we want to decrement the whole thing, and let's fucking go. Okay, so it was 2 iterations. We didn't provide the maximum amount of iterations, but apart from that, everything seems to be fine. Right, so let me see. We can explore the BPE table. So as far as I know, I have utility BPE inspect, right? So this is the utility. I can provide the input of BPE. So this is going to be small, 1 BPE. What do we have in here? Okay, so it's basically from 0 to 255 is just basically ASCII, all of the ASCII plus some of the unused characters in here, but doesn't matter. And the only frequent pair in here is actually BC. Yeah, and it's fair. So that's basically what you get in here. So this is in place. I would love to maybe test this thing without, like, with just a previous algorithm, but I don't have a way to quickly switch between them. Right, so so here's the Discord log, right? So we can try to run it on Discord log and just like see if it makes sense there. Okay, so let me give it a try. So where is the temporary thing in here? And I'm just like running it. Is it faster? Wait, I think it is faster. Just a second. So we save this entire thing to here. So let's actually call it IP for like in place. And let me compare the logs. I think the logs are kind of important in here. So here we're gonna have Discord log IP.txt. So here is the log. Okay, so this is the multi-threaded version, right? And yeah, it is faster. Look at that. Like multi-threaded version is 0.15. And this one is okay. So, but just a second, like we need to confirm that it at least makes sense, right? So we need to confirm that because maybe it just like did some bullshit, right? So maybe it broke in the text, who knows? Maybe it like literally broke in the text. So let me try to do a BPE inspect on the final result. So how many iterations we have in here? So 100 iterations. So that's pretty cool. So BPE inspect, Discord. I want to take a look at the multi-threaded version. So 100 BPE. Right, so what do we have in here? Okay, so it kind of makes sense, right? So there's some tokens that we identified in here, like ing, things that like repeat like way too many times. Okay, let's try to do that on IP1. Does it make sense? Okay, right, so there's also, okay, so there's like pretty much the same tokens, it's just like faster. And the fact that BPE inspect managed to load it up, that means that the indices are in correct states, because BPE inspect actually does like a bit of verification when it loads up this kind of thing. Right, let me see. So when you load the pairs, right? So look how much verification it actually does. Like it verifies that the size of the file is correct, right? It verifies the prelude, basically the stuff from 0 to 255, and that it makes sure that the indices within the pair point at the right thing. They don't overflow anywhere, right? If anything goes wrong in here, it will actually fail immediately, right? So there's a lot of checks in here. And the fact that it manages to load it up means that at least it is like passes the sanity check, right? At least it passes the sanity check. So we can actually do something interesting in here. We can try to do SHA-256, right, on all of the files in here. So we can do something like tkn and BPE, right? So just like compute all of that. Might as well, by the way, just redirect it to SHA-256 sum, right? So just like save all of that into the separate file. So then we're going to copy that file to the IP and just like make sure that it produces the same kind of thing, right? So, all right. Okay, so SHA-256, and let me, well, this is not what I wanted actually. I wanted to do C, right? So, oh. Well, I mean, okay, it was, it was okay. Up until, can we sort this shit somehow? So SHA-200. Is it possible for me to sort lines? Yeah, it sorted it by hash. I actually want to sort it by like a file name, but I don't think it's like super easy for me to do right now. So what is the smallest number where it failed? I think it failed at, yeah, it failed at 70th iteration. So until 70, it was kind of fine, and then it failed somewhere there. Damn. Okay, so but it makes sense, right? So we look at what kind of tokens are stored in the BPE, and it does make sense, right? So if I do BPE inspect, and it's just like, yeah, we can output this kind of stuff. So Discord log IP 100 BPE txt, right? So I can do that. So then I can take a look at MT. Right. Okay, so I have these two files, right? So the outputs of the inspection, and we can just do a div between them, like a textual div, just to see what's the difference between the tokens in there. Right. Might as well just put this thing in here, and this one's going to be MT and then IP. Oh. Key EEC EC. Ah. Well, I mean, it's the same tokens, but it's just like in a different. Ah, wait a freaking second. Wait a freaking second. The order of iteration. Okay, so I completely forgot. I completely forgot that hash tables are unordered containers. They are unordered containers, and one of the things we do in this thing is just we iterating the hash table to identify the maximum frequency. And since in a multi-threaded version and not multi-threaded version, in an in-place version, we just work with hash tables differently, right? In multi-threaded, we constantly recreate it from scratch, and in in-place, we reuse the same hash table. The order in which you're iterating them is going to be different, and you may actually have the most frequent, like several most frequent pairs, right? So depending on the order, you're gonna actually pick a different one. Damn. Okay. So I really need a way to actually switch between like a multi-threaded version and in-place version, so I can actually check like a lot of hypotheses in here. So like, do I have like a defined something like in yeah? So let's introduce something like in-place macro, right? So which is going to be responsible for doing this kind of thing. All right, so this is the thing, this is the first computation. If we defined in place, right, if we defined in place, we're doing this single computation in here, like pre-computation, and that's it. So if we don't have in place enabled, we do this recomputation on every iteration. By the way, let me mark this thing as enable threads, and this one as in place. Okay, so this one is done when in place not enabled, and this one is enable threads. There we go. Right, so this part is the same regardless of whether we're doing multi-threaded or in place. So all of that stuff is the same. And in here, okay, so if defined in place, we do that. We just do that. Otherwise, we have to do something else. So this is going to be endif, and this one is going to be else also for in place. So I need to recover this algorithm. But without in place scheiße. So how do we do that without in place scheiße? So we don't do any of that stuff. In fact, we don't do that. We don't do that. Yeah, so I think that was the original algorithm, actually. So now I should be able to recreate this kind of stuff. Okay, so I do have in place. Let's disable in place. So now I want to do txt to BPE, and where I'm going to saving that, I'm going to be saving it into MT2 right here, right? So because I want to make sure that I managed to recreate multi-threaded algorithm correctly. Hopefully I did. So we might as well also. I think I did because it's slow, right? So I think this is a single-threaded algorithm. Right, so let's kill this thing. Let's kill this thing because I disabled threading. Enable threads. Right, so let's just quickly enable threads. And I'm gonna do MT2. Yeah, one more time. One more time. Yeah, so it's faster and it's multi-threaded. We can take a look at BitTop. It utilizes all of the threads. Yeah, so it utilizes all of the threads. I can see that already. So that's pretty cool. Okay. So the reason why I want to do that is just like I want to put like hashes into this folder and just see if it's the same. So I just want to make sure that I recreated it correctly. So this is the second one. I copy paste SHA in here. So this is what we expect in terms of the state. SHA 256. All right. Okay, that's cool. So now I'm going to enable in place back. I'm enabling place back, but I'm disable also the threads. So what do we want to do in here? How can we make the order of iterating the frequency table basically predictable? I have the following idea. So essentially, we can use, when we're finding a maximum, we're using frequency not only as key, right? We can use the key of the frequency table as also the thing that we're iterating with. Like, how do I say that? Right, we taking the maximum between the frequencies and the key. Right, so introducing key actually makes it reproducible between all the threads. All right, so essentially you have a situation when these things can be equal to each other. So right now one is greater or not, but then you have a situation when they're equal to each other. And when they're equal to each other, right, what we do, we need to compare the keys in here. So we can actually use memcmp, right, and we take this thing, take this thing, and now let me maybe put the stuff in here. So we have to actually take a point in here. So, and if the frequencies are equal, we take in a maximum between keys already, right? And so if ice is greater than max value, only then we're reassigning it like that. All right, so that will hopefully make it a little bit more consistent, right? So I'm gonna remove MT2 because I wanna rerun, actually wanna rerun this stuff with multi-threaded. I disabled multi-threaded, but I think I should try to do it one more time. Right, so because it's gonna create a completely different order. Right, it's gonna create a completely different order. Ah, fuck! So memcmp, too few arguments. I also have to provide the size of the value in here. I completely forgot about that, so it has to be size. All right, so yeah, so let's actually recompute all of these things. So only 100 iterations. Damn, it's pretty slow compared to in place, actually. It's pretty slow. Okay, so this is the second one. And if I put the hashes from the one where we didn't compare with the keys, some of them should fail. So I expect them to fail. Actually, none of them failed. Huh, that's pretty surprising. Okay, so accidentally it may happen. I don't see any problem with that. Accidentally it may happen. Okay, so now in place, I'm enabling place, disabling the threads. Right, and now what we're going to be doing, we're doing the same thing, but we're saving into IP2. Okay. That's much faster. That's like, it's kind of surprising, right? So it's basically, I remember reading about that in CLRS, right? So introduction to algorithm, introduction to algorithms, right? So, and essentially, even in the intro of this book, they said that algorithms are technology, just like computers, because a better algorithm will perform better on a shadier computer than a shady algorithm on a supercomputer, right? And they even provided like a numbers, like actually proven mathematically that that could be the case. just like a log n algorithm is always going to be better on a shitty computer than exponential algorithm on a supercomputer. It's just like it's in the numbers, right? So, and there you go, right? So single core is beating 16 cores just with a better algorithm that just does less. So yeah, basically computer science 101, computer science 101. People quite often forget about that. So especially in the corporate world, they think that they can just throw more compute at a problem, right? When in reality, you can just like have like a better algorithm and a shittier computer. DeepSeek, by the way, just saying. So anyways, right, so we recomputed everything in here, and I'm going to open this thing and just like take the hashes in here and put SHA-256 and just like let's verify that everything. No, it didn't actually. No, it's still fucked up. That's bizarre. So did I do a fucky-wacky? I think I did a fucky-wacky. So memcp cmp. If this thing is greater or the values are equal, and then the value, of course, god freaking damn it, keys. I even said that I want to compare keys, but I compared the values anyway. That's why the hashes in empty2 were the same. Okay, I should have actually taken it as a warning sign. Anyway, so yeah, kill all of that stuff. So enable threads, don't enable in place. Right, so let's do empty2. There we go. All right. So multi-threaded. Okay, waiting a little bit, just waiting. Ran out of tea. Get freaking already streaming for almost an hour, by the way. Quickly check an idea. Freaking classic. Okay, so empty2 hashes from empty1. So yeah, so this is the one. Okay, some of them must be broken. Please be broken. No. Okay, again, accidentally it may happen. Sure. So now let's remove IP2. IP2, and then txt to bp. We need to go here, so this is in place. So we're enabling this kind of stuff back. So IP2, let's fucking go. Damn, so fucking fast. All right, so let's go here. So this is that. Fuck yeah. So I wonder, like, will it finish right on the session, right? So if we remove essentially the limitation, right? So if you don't provide the maximum iteration, it will try to compress it as much as possible until the process stops, right? So let's actually see how it goes, right? Is it going to be consistent or actually there's something. So it starts at 0.7, right? And then as it continues, it kind of speeds up actually. That's a bit bizarre. I think it literally speeds up. Why does it? Well, it kind of makes sense because the input is decreasing, so you actually have to iterate less token on each iteration. So does that mean it's going to actually speed up over time? I think it's like slowly speeding up. Look at that. And also it's probably consuming like a lot of my space. Just a second, let's actually kill it. Right. So because it's dumping, yeah, every token file is like 100 megabyte, right? So if you take a look at the size of this entire thing, it's already 8. Okay, so let's not do that. Let's not freaking do that. Though we can actually do that per like once per 1,000 iterations, right? So if you take a look at the help, so here's the help, and there is a dump frequency. So right now it's 10. We can set dump frequency every like 1,000. You can't really see what the fuck I'm doing, but just a second. So like a dump frequency is going to be equal to 1,000, and I'm going to put it in here. All right. So it dumped once, and then it doesn't dump, it keeps recomputing, and it's gonna only dump it every thousands, which I think it's a little bit more reasonable. Right, so we'll just wait thousands duration, and then we'll see. Damn, this is actually much faster than it was going when I was like training it off screen. So this is much better. So I think that's the way to go. That's actually the way to go. Okay, so as you can see on thousands iteration, it just generated this thing. And now while it is training, we can actually take a look at some of these things, right? So we can already take a look at the thousands of iteration while it is training. So inspect, BP inspect, Discord log, 1000 BPE. So it's better maybe to run it like this. Yeah, what do we have in here? There we go. So here's, yeah, we already have Discord emotes, right? It identified some of the Discord emotes as the tokens because they actually occur frequency within the Discord. Let's fucking go. Let's fucking go. Right. So yeah, I can see sure is the most frequent word in the Discord log. So that makes sense. That makes actually a lot of sense. I really like that. Yeah, it's very Discordish. It's very Discordish. All right. So let's stop the entire process, and I guess I'm gonna finish the session in here, right? So I want to compress the Discord log to their limit until the process fully stops, and then acquire the BPE table for the entirety of the Discord logs of our server, right? So, and then we're gonna try to check an interesting hypothesis that I actually stated at the beginning of our series, is that this BPE table kind of infers an implicit grammar out of the text, and using that grammar, you can actually kind of generate like gibberish, right? So essentially you can use this BPE table as a Markov chains, right? So it's not going to be LLM or artificial intelligence or anything, but it's kind of interesting that just the tokenizer by itself already contains a little bit of the knowledge that was extracted from the training set in an unsupervised fashion. I think it's just kind of cool and kind of interesting. So that's basically the goal of this series, right? Okay, so I'm gonna go compress some text, and then on the next session we're gonna try to generate some gibberish, right? Sounds good? Sounds Gucci, Tamaguchi. Thanks everyone for watching. Have a good one, and I see you all on the next recreation programming session with a who, a Mr. Azozin, as usual. I love you. Mwah.